We're going to start with a very cool new reaction that you need to learn. We're doing the talking heads thing. If the talking head thing bugs you, get out a piece of paper or post-it note and get rid of me right now. One thing I can tell you is I decided to split this last mini lecture up into two. I think it was going to get too long if I didn't, and this way I've incorporated a couple of examples at the end that I think should be helpful. So let's get going. To start, we need to advance to the next slide, which tells us we are going to talk about a new Anti-Markovnikov reaction. This will be very helpful. So a little review. Here we have an unsymmetrical alkene. If we add bromine to it, in our good old-fashioned, say, Br2, CCl4, we know we get trans addition to the double bond. This is my electrophile. That's my nucleophile. We're good. And stereochemistry, anti-addition because of the bromonium ion intermediate. Looks good to me. So we know how to do 1,2 dibromo addition to an alkene. And that's the same thing as, say, bromohydrin formation. Now how about this reaction? Piece of cake. To do that, all we have to do is add HBr, right? Electrophilic addition, nucleophile attacks electrophile. You get a carbocation intermediate. Of course, you get the most stable carbocation intermediate. And there's our product. Next, what do we have? We have, this is new and different. So this is an example from chapter 25. How do I get there? Well, this you should recognize as the allylic position. Therefore, we're talking about allylic halogenation. So here we know that we need to use N-bromosuccinimide. So the conditions for allylic halogenation are using N-bromosuccinimide with that homolytic cleavage due to heat or light. We get a very low steady state concentration of molecular bromine, and that allows us to add at the allylic position, not at the double bond. Okay, I like it. And now, yes, a new reaction besides hydroboration that's going to allow us to actually put a functional group on the less substituted carbon. Anti-Markovnikov addition of H and Br. All right. Anti-Markovnikov addition of HBr works really well. And it was discovered kind of serendipitously. Turns out that if you add HBr to an alkene and don't really pay attention to the conditions, you get different products depending upon whether or not the reaction is carried out in the dark or in the light. Well, if it's carried out in the light, what you should be thinking is, H nu. Wonder if this is a radical reaction. And indeed, you would be right on, because there must be some kind of change in mechanism, because when I add HBr in the light, I get anti-Markovnikov. When I add it in the dark, I get Markovnikov. So even though we call it Markovnikov or anti-Markovnikov, the important take-home message is here in the yellow. No matter what the mechanism is, always the guiding principle is that the most stable intermediate is always formed. So don't get hung up on the Markovnikov or the anti-Markovnikov. Just remember, in an organic reaction, it's always the case that the most stable intermediate is formed. So what's going on here? What's going on here is that the most stable intermediate is now a radical, not a carbocation. So here is an example where we're adding HBr in the presence of peroxides to 1-pentene, and we get 1-bromopentane, the anti-Markovnikov product. Why? Well, we take our peroxide, which is our initiator, heat it up or add a little light, doesn't matter, whichever way you want to cleave that very weak sigma bond, and that will generate two radicals from no radicals, meaning that's our initiation step. And now we have radicals abounding, so that a radical is going to be looking for something to react with. Well, what does it have to react with? That's fairly apparent that what it has to react with is 1-pentene. So in the propagation step, your radical, it also has HBr to react with. 1-pentene, HBr. I think H-atom abstraction is always the more facile, more kinetically favored step. So propagation, H-atom abstraction, boom. We go from the radical of the peroxide to the radical Br dot. Now, what's that Br dot going to do? Well, another propagation step. And now it can react with HBr as well, of course. So that's just, an equilibrium where you're just going back and forth. But eventually that Br dot says, oh, look at that 1-pentene. What can I do here? Now this is where it could get a little confusing. Yes, and we'll explain this in a minute. But basically what's going to happen here is that your Br dot is going to add to the alkene. It's not going to do an H-atom abstraction. Well, more on that later. But basically, Br dot now adds to the alkene. What do you get? You get the most stable intermediate, the secondary radical. So we would not see, in this reaction, we would not see Br dot adding to give me this radical, because of course that's primary, and it would be much less stable than the secondary radical. Alright, so once I have that intermediate radical, what can happen next? Another propagation step, plenty of HBr floating around. So H-atom abstraction again to give you your final product. Alright, Anti-Markovnikov addition, yippee skippy, works wonderfully. Now, here's the confusing part. Why doesn't the bromine dot react and remove the allylic hydrogen, so that this example would be another way to make to do allylic halogenation or something like that? Well, the answer is it can and it does. So what we've got here is a competition. Br dot either adding to the alkene to give us a secondary radical, or Br dot plucking off the allylic radical, as we've seen it do in the previous examples with NBS. In that case, what do you get? You get the allylic radical, which of course is even more stable. Well, that makes good sense, and you should be perfectly comfortable thinking that that could happen, because it can. But here's the deal. If the Br radical removes an allylic hydrogen, what you end up getting is that allylic radical that doesn't have anything to react with. The whole key to success in the NBS reaction, where NBS gives you the allylic halogenation product, is that allylic radical has a small, steady state concentration of Br2 to react with to make the allylic bromide. There is no Br2 present in the HBr addition, Anti-Markovnikov addition of HBr to an alkene. So in the absence of any Br2, this allylic radical is just in equilibrium with the Br dot and the alkene, and again, eventually, that happens to give you this, and as soon as that secondary radical is formed, H-atom abstraction happens very quickly to give you the Anti-Markovnikov product. So, how does this help us? It helps us a ton, because as you know, sometimes we want to put the functional group on the less substituted carbon. So for example, How could we make this molecule from toluene? Well, first problem here is, as usual, what the heck is toluene? Toluene is this guy. And when you see toluene, you say, that's just a hydrocarbon. Hydrocarbons don't do anything. Oh, but perhaps I could do some radical chemistry, like functionalizing at the benzylic position. All right, so working backwards from our target, it stands to reason that the obvious disconnection is right there, because right here is my toluene. Okay, so I think I will add this guy, which I'm very familiar with as a nucleophile, to this guy, toluene, as an electrophile. And what do I need to put on that question mark to make it an electrophile? A good leaving group. So let's make it a good leaving group. How about we put a bromine on there? I like it. All right, so once I do that, boom, I've made my target. Makes me happy. Now all I have to do is go from here to here, and you know what the conditions are for that. Radical chemistry, NBS, a little heat, and you're good. So that's how it helps us. It helps us keep this synthesis very short and concise. How about making this from 2-chloropentane? All right, let's start at the beginning. Based on our previous example, it makes sense that there's going to be a disconnection there. That's the only thing we've seen with alkynes. I think I'll just start working backwards. I'm not even going to pay any attention to the starting material. So we're going to have this. We're going to react it with 1, 2, 3, 4, 5 plus CH3, CH2, 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 1, 2, 3, 4, CH2Br. And why not? That ought to work. Okay. How do I make this? Well, now I ought to be able to make this from this 1, 2, 3, 4, 5 HBr. How about some peroxide? Let's randomly choose a peroxide and a little heat, and that ought to work. Yay! So now the question is, how do I make this from this? And I'll leave that one to you. Clearly, I need to make this 2-chloropentane undergo an elimination reaction that will give me the non-Zaitsev product. So you have to think carefully about what kind of reagent conditions you can use to make sure that when a beta hydrogen is removed, it is one of these purple ones and not one of the green ones. So that ought to do it. We will wrap up chapter 25 in the next mini lecture with a little bit of information about dissolving metal reductions, which are very cool, literally and figuratively. See you in class.